Okay, so our next speaker is Bob Wald. He will be telling us about memory, infrared entanglement, and the idealization of scattering from infinity. Thank you.
Okay, is the sound pretty good, or it's hard for me to tell? So either it's good because nobody's complaining, or it's terrible because no one can hear me. I'll assume it's good. So I want to tell you about, well, you've heard a lot about memory, but I want to tell you mainly about some things, at least that I found quite surprising regarding infrared entanglement and what I will, explain as sort of the idealization of scattering from infinity. So what I'm going to tell you is a fair amount of it is in a paper with Kartik Prabhu and Gautam Satishchandran, and the rest of it is work that's still in progress with Dane Danielson and Gautam Satishchandran. So you've already heard a lot about the memory effect. If we have some gravitational wave normally incident on this screen and have an array of test particles, they will oscillate into, an elliptical form in one axis, and then, elongate the opposite axis and oscillate that way. But when the gravitational wave has passed by at order 1 over r, there may be a permanent displacement of these particles. So that's what's referred to as the gravitational memory effect. A better way of, though, thinking about this, or at least describing it, rather than talking about these particles being displaced to one another, which they are, is work with coordinates where the positions of the particles are fixed, but the metric, the angular components of the metric, if we have a radially propagating gravitational wave, are changed at order 1 over r. And this is not any phenomena special to gravity or anything of that sort. In really any wave equation, in arbitrary even dimensions, odd dimensions are different and they don't have this memory effect, but at least in terms of what I'm going to describe, if we introduce Bondi-like coordinates, right now we could perfectly well be in flat space-time, the radiation in d dimensions will fall off like 1 over, this is d space-time dimensions, fall off like 1 over d over 2 minus 1, and Coulomb fields fall off like 1 over d to the 1 over r to the d minus 3. The Coulomb fields, I just mean static, solutions to Laplace's equation. So for any kind of massless fields in even dimensions, there will generically be a memory effect at Coulombic order, meaning that the field at late times at this Coulombic order will not return to its early time value generically, as I was just illustrating in the gravitational case. What is a remarkable fact about 4 space-time dimensions is if you put in d equals 4, both radiative and Coulombic orders are 1 over r, and so the memory effect gets inextricably intertwined with radiation. And this is the entire, as I'll explain very shortly, the entire origin of infrared divergences when we look at this kind of phenomena in quantum field theory. So just to get a few definitions in, I'm going to let h mu nu be the deviation of the metric from some flat metric at order 1 over r, and everything that I'll be essentially everything I'll be talking about will be at order 1 over R. The memory tensor is just the difference in the angular components of the metric at asymptotically late retarded times, that's at null infinity, that's I plus, or asymptotic time-like infinity, versus asymptotically early retarded times or at spatial infinity. And this is, of course, the same thing as integrating the Bondi news from early to late retarded times. Now, as I've already emphasized, this existence of a memory effect is not at all special to gravity, and for any other massless field like electromagnetism, you'd have similar memory effects. In the electromagnetic case, the electromagnetic memory is similarly the difference in the vector potential, the angular components of the vector potential at late and early retarded times, or equivalently the integral of the electric field. And just as the gravitational memory can be described as a permanent displacement of a family of test particles, electromagnetic memory would correspond to having a single charged test particle receive a net momentum kick after the passage of a gravitational wave. Well, the connection with infrared divergences just comes from the fact that if you have this kind of memory offset of the field from early retarded times to late retarded times, then when you take the Fourier transform of an object with a step of this sort, you get a 1 over frequency behavior at low frequencies. And the relevance of that is, well, when we're constructing some out ordinary Fock space of states, that's sort of based on a one particle Hilbert space that you get by looking at positive frequency solutions at, in this case, future null infinity. Of course, there'll be a same story for past null infinity. And introducing a norm that is based on this, well, that is the Klein-Gordon norm that's kind of based on the symplectic product. The Klein-Gordon norm asks you to take the Fourier transform of your solution, square it, multiply it by omega, and integrate over frequencies. But if the Fourier transform at low frequencies is going like 1 over omega, you're going to get an integral of d omega over omega at low frequencies, and that will not give you an infinite Klein-Gordon norm. So states, if you're looking at some coherent-like state corresponding to a classical solution of this sort that has a memory effect of this sort, that is not going to be something representable in the usual Fock space. It will have infinite norm. There's absolutely nothing wrong with such states, and they will unavoidably occur in scattering theory. But if you try to stuff them into the usual Fock space, you're going to get infinities coming in. So rather than stuffing them into the usual Fock space and have infinities coming in, I mean, these states with memory should really be treated as legitimate states, as they are. And they naturally live in, well, unitarily inequivalent Fock representation. So we can construct a Fock space of states Well, here I'm talking about the electromagnetic case, but you can do exactly the same thing in the gravitational case. By taking the usual Fock representation, but replacing the field operator by itself plus a multiple of the identity, where this object is a classical field with whatever desired memory you have. And of course, you can get states with memory that have arbitrarily low frequency. So we can make sure that, you know, any energy or other effects of this object that we're using for this construction is as small as we like, but it will have, of course, this desired memory. And this will give then a representation of the field algebra that, well, will have a Fock-space structure, although it won't have any, you know, the choice of vacuum will depend on your choice of classical field with memory. But, you know, this will allow you to realize your state with memory as a completely legitimate finite norm state, but in a different Hilbert space. And you can do exactly the same thing in the gravitational case. Okay, so now, yes, Andy.
When you say it's in a different Hilbert space, there are operators that take you from one memory vacuum to another memory vacuum. So why would you say it was?
Yeah, so, yeah, this is something.
They're not super selection sectors.
When you say memory vacuum, it isn't clear whether you mean.
Well, it's not my word, it's your word. But
well, yeah, okay. But I mean, there would be what used to be the vacuum state now would be, you know, essentially a coherent state corresponding to this classical solution with memory. But this is not, you know, a new vacuum that just differs by a, you know, a large gauge transformation. This is a really different state, and this has memory. If you just apply a large gauge transformation to the vacuum, I'm about to get to large gauge transformations, that would still be a state of zero memory. Now, we should talk about this.
Would you agree it's a system in which there's an infinite vacuum degeneracy?
Yes, but that's not what I'm referring to here. I mean, this is not degenerate with the original vacuum. This is a physically different state. But you can construct, you know, zero memory Fock space states that are differing just by large gauge transformations. Those would be degenerate. This is the issue I, you know, was briefly talking to you about, which I still find a bit confusing in terms of what people say and mean, and it might be great if we discuss this further. Go ahead.
We just had a lecture on how to measure it. So,
this is measurable.
Yeah. So if we talk about measurable things, everyone will agree, I guess.
Yeah, okay. Yeah, feel, well, free to jump in at any other points as well. Okay, so there's some further things that, well, that play a role in the story that I'm about to tell. So, you know, further leg of the or vertex of the Strominger triangle, having to do with asymptotic symmetries and also gauge charges. So if I start with the E&M case, if we do a gauge transformation by changing the vector potential by the gradient of a function that's purely a function of angle and doesn't have any radial or time dependence, so this doesn't fall off at infinity, but the gradient will still fall off like 1 over r. that will preserve the asymptotic conditions on the vector potential. But even though I called this a gauge transformation, it technically differs from a gauge transformation that falls off at infinity in that it is not a degeneracy of the symplectic form. So it would count as a symmetry of the theory rather than gauge, and shouldn't be kind of, factored out of the phase space. And these symmetries have charges associated with them. You can define the charge actually at an arbitrary retarded time. It's just the 1 over r squared, that's what the 2 means, part of the electric field, but weighted with this arbitrary function of angles. Now, having an electromagnetic field with memory, we don't have any radiation at early and late times. So in fact, the vector potential at early and late times, or at late times, differs from that at early times by a large gauge transformation. And there is a relation between the memory that I defined here in the electromagnetic case, and these large gauge charges, which is given by the formula that the memory, the electromagnetic memory is just the difference between these charges at asymptotically late times minus, whoops, that's the problem with these buttons being too close to each other. I'll have to be a little more careful. And if you have a flux of charge through null infinity, there will also be a contribution that it will give to the memory. The charge at future time-like infinity would be determined entirely by the trajectories of outgoing massive charge particles. Yeah.
Just to clarify the reply to Andy before. So here, before you seem to be saying that a large gauge transformation cannot turn on memory. Now you're saying that memory corresponds to, a large gauge transformation. But I think you meant turn on gravity. I mean, you cannot turn on memory just with a large gauge transformation because you cannot turn on gravitational waves just with a large gauge transformation. Is that
yes, that's what I was trying to say earlier. But if you have electromagnetic or gravitational waves, that may be interference of the two mics, yeah. If you have gravitational waves, then that will generically introduce a transformation from what you might view as, some vacuum before the gravitational waves turned on to another vacuum after. Right, that is, thank you for the clarifying question. So I've written the electromagnetic formulas here, but the situation is exactly analogous in the gravitational case. And in particular, if we do super translations, which are just diffeomorphisms, so those are gauge, but in fact, they're gauged, those diffeos are not degeneracies of the symplectic form, and they count as symmetries, and they also have associated charges that can be defined at an arbitrary retarded time that involve the 1 over r cubed electric part of the Wald tensor instead of the 1 over r squared electric field in electromagnetism, and also have this additional term in the gravitational case. And again, if you have some non-trivial gravitational radiation with memory, but the radiation is non-zero. Oh, yeah, that was a problem yesterday too. Okay. Thank you. If you have some non-trivial gravitational radiation with memory, the memory at the state, the HAB, I should say, at early and late times will differ by a supertranslation. And again, there's a relation between the memory and the charges at late and early retarded times, together with in this case, the gravitational flux, which would be the Bondi flux. Well, if there's other massless particles in the fields in the theory, there would be potentially contributions from that as well. Okay, so the object that is going to be important for the rest of what I'm saying are the charges that I just described at spatial infinity. And if I take I'm working with the electromagnetic formula, but if I just take this formula and put the QI naught on the left side instead, the charge at spatial infinity is the charge at time-like infinity. This flux term, if there's charge flux to null infinity, and this memory term. Well, if you look at what this memory term, this observable, does on phase space, it actually generates the large gauge transformations, in the sense, the classical mechanics sense of, observables generating vector fields, or vector fields being associated with observables. It generates the large gauge transformations of the electromagnetic field. This would generate the large gauge transformations on the massless charged particles coming out to scry. And this generates gauge transformations of the charge fields, the massive charge fields that would propagate to time-like infinity. So this object is in fact the full generator of large gauge transformations on all the fields. And well, you can say the same thing on scry minus about the Q in at I minus. Yeah, where am I on this? Right. So yeah, so this is true both in the electromagnetic and the gravitational case. I mean, I have the same sort of formula here in the gravitational case as I have in the electromagnetic case. Okay, so now there are a number of things that are important about these charges. One of them, which will not actually play any role in what I'm going to say further, is that under suitable asymptotic flatness assumptions, you get an antipodal matching of these charges between scry plus and scry minus at spatial infinity. The thing that will play a big role in what I'm going to say in the rest of the talk is the superselection aspects of these charges. And I'm going to focus now on the electromagnetic case. I'll return briefly to the gravitational case in the last couple of slides. So let me now step back and, what are we, how are we describing physics? What are we supposed to be doing? Well, I'm taking the viewpoint that what we're really interested in is sort of local experiments performed in the bulk. And in the electromagnetic case, anything that we're talking about and measuring should be described by some local gauge invariant observables. I mean, they could be Wilson lines and so on. They don't have to be, you know, but the field tensor or the charge current or whatever, and so on. But they should be describable in terms of gauge invariant observables. But the large gauge transformations are completely indistinguishable from ordinary gauge transformations if I'm restricting to some local region away from infinity. So any local gauge invariant observable that I would want to use to describe physics in my laboratory, I would claim is going to have to commute with this generator of the large gauge transformations at spatial infinity. I mean, one could also argue this just from the fact that this is an observable near spatial infinity, which is going to be space-like related to whatever observables I have in my lab, so they should commute on those grounds anyway. But this implies that the eigensubspace of the large gauge charges are going to define superselection sectors for gauge invariant local observables. This is something very, yeah.
Do you include, I mean, the memory effect is the difference between something at plus infinity and minus infinity. So it's not local, it's zero. I mean, yeah, in some sense it's zero momentum. So do you mean here to be excluding that as an observable?
I'm going to want to consider asymptotic observables, but I want to, here, the O is supposed to be some laboratory observable. So yeah, I'm not saying this commutes with with all of the asymptotic observables at null infinity, and I do want to talk about them and use them. But what I want to say is that for some observable appropriate for a laboratory experiment that I'm doing in some finite region, those observables, and I'm only talking here about those local gauge invariant observables, have to commute with these charges.
So is the memory a local gauge invariant observable?
No, memory is some object at Scri plus that is not at all, well, it's gauge invariant, but it's not, it would not count as a local observable in this.
But we're planning to. We should.
It's a exactly like nobody has ever seen a
No.
space transition. But we do believe that space transition, like water boiling, is a good approximation.
But if we see this thing go up and down, if we see the wave goes up and down,
Nobody has ever seen it. Nobody will see it.
I totally agree with you. I totally agree with you, Massimo. But nobody's ever seen anything for certain, right? So if you have a wave that comes up and down, and the time scale of the wave is 100 nanoseconds, and you wait a year, and it doesn't come back, you think, okay, a year's infinity. That's what David is planning to do.
Yeah.
So.
But nobody, we know that water boils, but we cannot say that we observe phase transitions because of the pop as a finite size.
I totally agree with you, Massimo.
Take this abstraction of it.
Yeah, so if you're doing the LIGO experiment, then so again, I'm only talking about the electromagnetic case here, but yeah, if you're doing some laboratory experiment like LIGO and so on, then that is in the context that I'm talking about here. But then then one could argue about whether you are measuring the memory at null infinity or whatever, but
So to be
In ordinary quantum mechanics, we often talk just the very existence of an S matrix, particularly when you start talking about infrared divergences. We make the assumption, which is wildly unphysical and unrealistic, that we can talk about an initial state with arbitrary infinite precision and evolve it to a final state with arbitrary infinite precision,
Yeah.
to know all the laws of physics.
So I'm not concerned, I mean, I'm not challenging that, I mean, or I'm not
Yeah.
objecting to those idealizations. As we'll see, I will be getting to the idealization of taking states all the way out to infinity. But,
Okay, thank you.
but that will be part of the story that will flow from this. But right now, I'm just talking about what you would, but yeah, I think the next slide, I think will probably help a lot in terms of clarifying what I'm saying and possibly raising new objections. So I'm making this assertion that we have super selection rules on local gauge invariant observables. Again, I'm specifically talking about the electromagnetic case. And it's not really very different from the ordinary charge super selection rules that I think everyone would agree with. Okay, but this is, now we're getting to the rather strange stuff that I want to elucidate and explain. One consequence is that if I could imagine as about the most trivial thing I might do from infinity of sending in one electron in a normalized ordinary Fock space state at past time-like infinity and no electromagnetic radiation at all. And one could ask, what does that look like in the bulk? Well, you might say that looks like an electron, but it doesn't. It doesn't, in fact, look like anything in the bulk. There is no, starting with bulk states, there is no asymptotic state producible, again, starting with normalized physical states in one's laboratory in the bulk, you can't get a bare electron. So let's start it this way of what does a bare electron look like sent in from infinity look like in your laboratory? Well, again, we have, with no electromagnetic radiation, the charge at spatial infinity is going to be the incoming charge, but the incoming charge has continuous spectrum, and its eigenstates are, in fact, plane wave states. So there would be a complete decoherence into these plane wave eigenstate states, which in particular would imply translation invariance of all of the gauge invariant local observables that you have in the bulk, but there isn't such a state. So bare electron incoming wave packet states, normalized states, I'm not talking about non-normalized plane wave states, which would be eigenstates of the charge, and that's what the bare electron wave packet states just do not describe physical. So what would describe an incoming state in the bulk? I think after I do this slide and the next, I think I should do another simple, more explicit example on the board to illustrate what I'm talking about. Well, we're going to need to get eigenstates of the charge at spatial infinity. We can do that by entangling every momentum mode of incoming electron states with incoming photon states of a compensating memory, because then these two terms will cancel. and you'll get an eigenstate of, well, let's say 0 charge for simplicity at spatial infinity. So if you pair incoming plane wave states with photon states with memory, again, these are formally eigenstates of the charge at past time-like infinity. If you pair them with photons in these memory states, and then do this for each plane wave state, take a appropriate direct integral over the p's and Fock space direct sum over the n's, you'll get now a Hilbert space that will not suffer from this superselection situation, because it is already superselected as an eigenstate of charge. And this is exactly the Fadeev-Kulish construction, and adding these states with memory, incoming radiation incredibly entangled with the incoming electrons is what's referred to as dressing the electrons. So this is possible incoming state to produce, but if you think of it the other way, if you have a state in your laboratory, I claim if you let it propagate to infinity, it will evolve, in fact, to a Fadeev-Kulish state. So imagine that we have an electron in a trap that had been held in that trap forever. But now at some finite time, we release the electron from the trap and let it propagate freely to infinity. So prior to our releasing it, there's no electromagnetic radiation. And you might think, well, I release it, we just have a free electron propagating out to infinity, but releasing it is going to result in some electromagnetic radiation. Now you might think, who cares that electromagnetic, I can release it slowly and carefully. There's essentially no energy radiated, but in fact, you cannot avoid emitting a lot of soft radiation in its release. And that will result over infinite time in a complete entanglement of the different momentum modes of the electron with soft photons, and the asymptotic state, I claim, will be a Fadeev-Kulish state. Now, this is totally irrelevant for any laboratory physics. It's only relevant for the asymptotic description of states, because this is a this decoherence effect is logarithmic in time and is completely negligible if you put in any sort of numbers, and I'll do that right now, in terms of what actually happens in laboratories. In other words, I'm arguing that there is a major difference between the behavior of a free electron at the late times relevant to a practical experiment as compared with the infinitely late times that occur in scattering theory. So let me, since I think the audience is probably finding this at least as strange as I am, but I'm more used to it. Let me give some simple example. Let's suppose we have an electron in the laboratory, some wave packet that we managed to split into two components with different momenta. And we let these components drift along, and there's a relative velocity v, let's say, between these components. We turn them around at some point and recombine them here. And so this is kind of like a two-slit experiment, really. And I want to know whether I get interference between these two components. So, there's going to be some acceleration and some different differential radiation emitted in this turnaround. We can estimate that with the Larmor formula. The energy will be, let's say, tau is some turnaround time. So the radiated energy will be something like that according to the Larmor formula. And this will go on for a time tau. And if we imagine that the photons are all coming out at a frequency 1 over tau, there'll be another, if I want to know the expected, entangling photon number, I'll get the estimate in doing it this way of Q squared V squared. And if I make, QV small or whatever, I can keep the electrons coherent, and anyone doing some experiment of this sort definitely would do that. But this is incorrect. The number of, I'll leave this in here, but the photons don't just come out at frequency tau or 1 over tau. You get frequencies going down, to as long a time scale as comes in here. And if you do the calculation, you can do this just using the Leonard-Vickert formulas, but taking into account the Coulomb-like effects in the potential, which is what is relevant for this. You're going to get Q squared V squared log of T over tau coming in as the final estimate. So that means if I wait long enough, let these drift out far enough, I do the same turnaround, bring them back together. These electrons beams are not going to interfere. They're going to be completely decohered if I wait long enough. There is no way any laboratory is going to wait long enough to do that. But if you're going to describe, scattering theory in terms of the infinitely late times, this is going to be an important effect, and it's going to completely decohere your electron in your laboratory, and it would make it into a Faddeev-Coolidge state. So one might ask then, why does scattering theory work? Yeah.
In any momentum eigenstate with equal probability?
No.
What does it mean by
probability distribution in momentum won't change at all? But there will not be any interference between components of different momenta. So again, this is maybe the best illustration. If I've waited long enough for this factor to be big, which means the electrons would have gone way out and come back in,
I see.
there will not be any, wiggly interference effect when I combine the electron and look at it on a screen.
So in a momentum basis, it's just diagonal, but
yes,
but the entries are not depend on the momentum.
Yeah. The entries won't change their values, but there just won't be any interference effects.
And those are computable somehow?
And
the function of momentum is somehow computable?
Well, it's whatever you started with, because none of this radiation and so on is going to have much of an effect on any of the momentum components. It's all very low frequency radiation and very little of it. I mean, very little of it except photon number. Okay, well, I'm running a bit low on time, but let me just, you might think what I'm challenging use of scattering theory at all. Well, first of all, nobody's going to send in an Faddeev-Coolidge state, and you would do calculations sending in bare electrons and so on. But I mean, if you are looking at what's going on in finite time, well, then these decoherence effects are not going to be significant. If you can then, for the purposes of doing the calculations, replace your incoming electron wave packet as though by a plane wave. This isn't really the kind of scattering experiment one might be doing, but you can do that. And now with the plane waves, you can take them out to infinity without any problem. So if you stick with plane waves, you can go to infinity. Just don't do wave packets and try to go to infinity, because you'll completely lose the coherence of them. Now, of course, when you, even working with plane waves, you're going to get memory effects in the radiation, but those can be dealt with in the usual fixes that people use to do inclusive cross sections. Okay, so the Faddeev-Coolidge construction works fine in massive QED, but if you try to do the same construction in massless QED, you run into a further problem, which is directly related to what are referred to as collinear divergences. The problem here is that the electric field of these eigenstates now has sufficiently singular angular behavior that it's going to cause infinities in the stress energy tensor. So you can construct mathematically analogous Faddeev-Coolidge states, but they are unphysical. And my expectation is, but it's only a expectation, we haven't shown anything, is that quantum scattering theory from infinity, again, it's from infinity, that's for massless charged fields probably doesn't make sense. Very surprisingly, because there's no problem with classical scattering theory, but there don't seem to be any candidates for physical incoming states. At least I'm not aware of them. Okay, so now the gravitational case, I'll easily do that. There'll be plenty more time for discussion because I have incredibly little to say about the gravitational case. Well, so linearized gravity with a massive field source, well, okay. Yeah, okay. Yeah, there isn't a particularly big problem with linearized gravity with a massless, with a massive field source. And in fact, the collinear divergences that you get in linearized gravity, even if you have a massless field source, are not as singular and don't cause sort of stress energy type divergences. But in fully nonlinear gravity, it's actually, well, you can't produce Faddeev-Coolidge states at all, nor can you produce eigenstates at all of the supertranslation charges, right? There's a simple argument that only the vacuum is the only eigenstate of supertranslation charges. The problem can be understood that if you dress incoming gravitons with other gravitons, which you'd need to do to try to make a Faddeev-Coolidge-like eigenstate of charge, these additional gravitons will contribute, well, maybe a really tiny bit to the Bondi fluxes, but that's enough to spoil this eigenstate property. And again, I mean, you might think maybe you could get some convergent series, but there's a simple argument that you can't make any eigenstates at all of these charges. But the contradiction that this would give is the argument that I was giving in electromagnetism here with the superselection, has to do with, in our laboratory, we have gauge invariant local observables, and those observables are going to get superselected. But in gravity, I don't know how to construct gauge invariant local observables that would have been subject to superselection. So I'm not sure what argument I can give that would say that there's a problem if we don't have eigenstates of the charges. If that sounds confusing and incredibly inconclusive, then I've communicated my thoughts very well. So it isn't obvious what should be imposed on scattering states. It's hard to imagine the situation would be better than, in electrodynamics or something, and that you wouldn't have to have all this soft entanglement to get physical states. But I don't have an argument to say that. So
where does the higher Gauss number that would be local engagement there?
okay, I mean, but I mean, what?
You can do descent and construct integrated operators that are non-local engagement, and you can construct form factors of those integrated operators.
Okay, well, why don't we talk about that further? So just to, this is actually my last slide, but I want to emphasize that scattering from infinity is, on account of exactly this problem, exactly this problem that with this log T that I'm talking about when you look at infrared entanglement in the bulk, involves an idealization, and it isn't, I mean, an idealization that one should be consciously aware of. So in classical field theory, there's just no problem, or I mean, no fundamental or basic problem in taking asymptotic limits of either massless or massive fields to null in the case of massless fields, and time-like in the case of massive fields, infinity. And the behavior of the fields at infinity give a good representation of the behavior of fields at the large but finite times that would be relevant for doing laboratory experiments. But in the case, it's very special to 4 dimensions and massless fields, this classical memory effect, which is, completely innocuous, I mean, interesting, but innocuous classically, gives rise to this sort of infrared entanglement that grows logarithmically, as I've illustrated here with time, and becomes infinite in the asymptotic limit. So the behavior of states at asymptotic infinity in this situation is very different from the behavior of states at large and but finite times relevant to experiments. So this isn't important, as I indicated, for practical calculations. If you want to know inclusive cross sections at given four momenta, you know, the scattering theory as practiced is entirely, you know, satisfactory for giving correct type answers. But if one elevates scattering theory to a fundamental status in the formulation of the theory, I think these issues should be kept in mind. What role they'll play, I don't know, but they are something I think one should keep in mind and be aware of. Okay, thank you.
Okay, thank you for the talk. Any final questions before we go for the break? Somebody wants to defend the S matrix from this assassination attempt? This one is better.
Oh, okay. I guess I disagree with the statement that classical theory is innocuous, because there's also inferred divergences classically that come from.
Well, they're not, I mean, the divergences are in Klein-Gordon type norms. I mean, that it's not important for anything I could think of classically that these norms would be infinite. You know, and higher Sobolev norms will be fine and so on too. I mean, you know, yeah, I don't, I mean, it's not, you know, one cares about it a lot in the quantum theory because you've got to normalize your states, but you don't have to normalize anything in the classical theory. Just get your classical solution.
I guess I still disagree, but.
I was so could you say a bit?
Is it still on? We can't hear you. Closer, maybe?
Could you say again why there are no dressed states in gravity? So what's the problem with fluxes again?
Sorry to say that I didn't.
You said that there's a problem with constructing dressed states, but the Coolidge states for gravitons because there are Bondi fluxes.
Oh, it's no. The problem I was alluding to, I think I didn't say this that clearly in that moment of the talk. You have a hard graviton. Okay, that's you know, a hard graviton wave packet. You have to dress each of the, you know, momentum components of that with soft gravitons. Okay, but now the soft gravitons that you're using, I mean, those are real, all these gravitons that I'm ever mentioned, whether soft or hard, those are real things. So they're going to contribute to the Bondi fluxes. They may be contributing tiny amounts to the Bondi fluxes, but that will give, you know, contributions to the charge at spatial infinity as well. So you need to dress the dressing.
Oh, there's some recursive.
But now you need to dress the dressing that you use for the dressing.
Oh, this
And you
won't
never
give
get
an
anything,
eigenstate of the charge.
so you never can make an eigenstate. And I wouldn't know how to make that argument precise, but there's a separate argument that you just don't have eigenstates.
Yeah, in higher dimensions, do all these problems go away, or are there any other?
Yeah, because there's no mixing the Coulombic memory effects in with the radiation, so you won't get these infrared divergences and
So the scattering theory is in perfectly good shape in higher dimensions, no problems at all.
yeah, I mean, at least, well, none of the issues that I talked about would occur in other than in 4 dimensions.
So you said this is not so much of observational consequence because of this time needs to be long.
Yeah,
So what about anything quantum cosmological? Like, so for any quantum cosmological consideration in any such calculations or observations, would this be a effect?
yeah, I mean, I don't think a Hubble time would be long enough for, you know, I mean, depending on what you chose for the relative, you know, velocity of separation, and you need to choose it in such a way that you wouldn't automatically get or quickly get decoherence just due to the radiation from the turnaround. But yeah, I don't know. I mean, I don't know how to describe incoming states from the Big Bang particularly. I mean, you know, the asymptotic flatness, you know, S matrix like ideas wouldn't, you know, as they stand, wouldn't be relevant for trying to describe cosmological initial states. So I'm not sure that's a helpful answer to your question, but you know, I'm not sure what the question would be if one was starting from a Big Bang. I mean, and asking about decoherence type issues and soft radiation. I wouldn't know how to describe any of those things, and one wouldn't have any of the machinery that I've alluded to in this talk.
Okay, any final question? If not, say Bob again.